Okay, so today we're going to start with principal bundles. Then we're going to link principal bundles with vector bundles that we did last time and study how the two interact with each other. So before we define principal bundles, so let's say the idea is that principal bundles are bundles with Lie groups as fibers. So this is in the same way that vector bundles, you can think of them as bundles with vector spaces as fibers. This is somewhat similar. And as we saw with vector bundles, when they're not just bundles with some vector space in the fiber, uh, but you also care about the vector space structure. So if you talk about morphism of vector spaces, you also ask that the maps are fiber-wise linear, for instance. And here, of course, we will have something similar. We're not just putting some Lie groups there. We will also consider how the Lie groups acts on itself. But we will see that in a moment. So let's start with the definition, which is not the definition of principal bundle, but is the definition of a right action. So we already defined an action of a group on a manifold or on a set in general. And that is sometimes referred to as an action on the left. But here I also want to find what is an action on the right. So we take a Lie group and we say that it acts on the right on a manifold F. And I'm calling this manifold F because then in our setup, this will be the fiber. If we have a map R from G into the diffeomorphism group of F is such that, so the neutral element, the node with E, is just sent to the identity map. And if we take R of G inverse, we take, this is equivalent to taking R of G and then taking the inverse diffeomorphism. And then we have this, so far we're kind of, this looks like we're defining just a morphism of groups, but this last one tells us that we're not talking about a morphism of groups. We have this kind of anti-morphism group in which you invert the order of the operation. Okay, so instead of GH, you do first H and then G. And maybe a small observation, which I'm sure you've already seen, but let's just recall it. So if we have a left action, so just an action is a left action. So just an action for how we defined it before. Then R of G defined as L of G inverse is a right action. Okay, because simply here you have, with the action, you have really a morphism of groups, but if you put inverse, you get this anti-morphism thing. Okay. And let's immediately start with our first example of such an action, which is important for us. So if we have E, a bundle with fiber F, which is diffeomorphic to a Lie group G, and structure group. So when you have a bundle, I have to specify the structure group. G itself, so G is a group, and we're just saying that each fiber is diffeomorphic to G. So this is diffeo. And it's important because these fibers are not groups per se. They're just manifolds, and they happen to be diffeomorphic to this Lie group. And then we can define a right action. Then G acts on the right on F as follows. So here we say that here we have a diffeomorphism. So let's give a name to this diffeomorphism, theta. So this is a diffeomorphism. Diffeomorphism. Then we define R G of F as theta inverse theta F G. So this theta F is an element in G. We just do this multiplication. This is a multiplication in G. Then we bring it back to F. Yeah? So this is our right action. So when I write this RG, this is, I'm gonna change color. What I mean by this is like R of G, and this is now an element of the diffeomorphism group, and we apply it to F. Yeah, this is how I define this R sub G. And this we will usually just write FG. Yeah, so for F in the fiber and G in the group. Okay, and of course, this is very much dependent on this diffeomorphism theta, because yeah, you can clearly just change this theta. You can take another diffeomorphism, and then this action is just different. But in fact, this is a right action, and it will be an important right action for us in the definition of principal bundles. So, in fact, let's define principal bundle. So we start with the Lie group and a bundle. And usually bundles, we call them EM pi, but this time we call them P M pi. P will stand for principal with fiber G and structure group G. Structure group G. So there's this thing, this intertwining thing, that the structure group is the same as the fiber. Is a principal bundle if there exists a trivializing atlas for M, of course, I mean, for P, sorry, not for M, U alpha, phi alpha for P, such that for every point in U alpha, if we take phi alpha and we restrict it to a fiber, so this Px is the fiber, so this is a map from Px, which remember is something which is diffeomorphic to G, because the structure group is G, into X times G, and so this is just by the definition of trivializing atlas. So what we want from this is to somehow respect this group structure. So we want this to be right G equivariant. What does this mean? Well, basically that it's that this action on the right kind of commutes. So let's just write down what it means, i.e. if we take phi alpha of V, well, this is gonna, we can write it as X, where X is just phi of V, comma, the second component. So if we write it like this, then the second component satisfies this. So if we take as an input V times G, so this is the right action of the group G on the fiber Px, which is diffeomorphic to G. This is the same as first taking the trivialization and then multiplying on the right. Yeah, this is just a multiplication on the right. It's not an action. Of course, a multiplication on the right is an action, but this is an, let's say, an abstract action. Well, here it's really just the multiplication because this is an element of G. Okay, so let's say where things are. So V is in Px and G is in G. And so whenever we have a bundle, we automatically have, not everywhere, but we do have an action of its structure group. This is really how the bundle is defined, because you need to be able to glue these trivializing atlases, and you do that using the transition maps. And to have a transition map, you need an action of the structure group G on the fibers. And here, so we have two different actions of G on the fibers. One is the one given by the fact that G is the structure group, and that is our left action, which we use for our transition maps. But then we also have this right action given by fiber-wise multiplication on the right. And the observation is that these two actions commute, in the sense that it doesn't matter if you first multiply by the left and then to the right, or first to the right and then to the left. So there was a smart way to write this. Yeah, this right action commutes with the left action given by the fact that G is a structure, given by the fact that G is the structure group. Okay, so I hope this observation is clear. And now perhaps it would be like a good time to give examples, but we're gonna postpone that a bit. I want to give you a few more definitions. For instance, the notion of morphism between principal bundles. So we take P and P prime principal bundle over M with structure group G. And here I don't have to specify what's the fiber, because by the definition of principal bundle, the fiber and the structure group are the same. So when we talk about principal bundles, we only specify the structure group or the fiber, and it's the same thing. And here we take a different manifold and a different structure group. So of course, the idea is that this should be a morphism of bundles, which somehow respects this G and G prime action. So we need to give a relationship somehow between this G and G prime, and this relationship is given by Lie group morphism. So we take Rho, a map from G to G prime, which is a Lie group morphism. So just a group morphism, which is also differentiable. Then we say that a bundle morphism, so this we know what it is. So this is just a morphism of bundles. FC is a principal bundle morphism. Principal bundle morphism. Sorry, principal bundle Rho morphism. So to remember this Rho, but of course that it's something we will kind of forget most of the times, because this would be somehow given from context. If from every x in M, we have, well, we have what we expect to have, and that is that if you look at V over a particular fiber, then this commutes. Sorry, not commutes, but it comes out. So this PG, it's an element of P, yeah, in particular of the fiber over X. And when you bring it outside, now this is an element of P prime, so we cannot act with just G, because we need an element of G prime, and this Rho tells us how to go from G to G prime. So that's what we ask. So this is for P in Px and G in G. And furthermore, of course, we also ask that fibers go to fibers. No, sorry, that's not something we ask. Never mind. And that's it. And as I was saying, yeah, we will omit this Rho whenever it makes sense to omit it. So last time when we did vector bundles, we said, yeah, that vector bundles are just bundles such the structure group is some GLN and the fibers are RK or R to some N. And plus some dislinearity properties. And we showed an example where we do have a fiber, which is the Euclidean space, and the group is GLN, but we do not have a vector bundle. Nevertheless, we were able to construct another bundle, which was a vector bundle, and which us bundle was equivalent to our given bundle, which was not a vector bundle. And here we have something similar. So if we have a manifold and just a bundle, this is not a principal bundle, bundle over M, fiber G, and structure group. So you really have to specify everything because it's just a bundle for now. Then there exists a principal bundle, and this is unique up to isomorphisms, P prime on M, which is equivalent to P as bundles. Yeah, so this is really the same as before, and the proof again comes. We had this big theorem that said that every time you have some transition functions and some fiber, then you can make up a bundle which is precisely those fibers and those transition functions, and this is how we do it. So having a bundle gives you some transition functions and of course some fibers, and if now you build another bundle, which will be our pre-prime, using that construction, you will actually see that all those maps are morphisms of groups, and the right action is preserved. So that's how you get this existence. And that same theorem tells us that this is an existence up to, which is unique up to isomorphisms. Okay. And in particular, we have, not here, but maybe from the previous proposition, there is so here we saw previous definition. So we have this Rho morphisms, and we have one very specific bundle morphism, principal bundle morphism, which is really important for us, and that is called the reduction of a bundle. So let's see what that is. So we start with a lead group and with a lead subgroup. And the Rho that from the previous definition, we just take the immersion. And we take P, principal bundle over M with fiber and hence structure group G, and P prime, same thing again over M and fiber H. And we say that P prime is a reduction of P if there exists a morphism of bundles such that this first component is identity. Morphism, not just of bundles, but of principal bundles, of course. So a Rho morphism, to be precise, Rho morphism of principal bundles such that H is actually injective. Okay, so here the idea is that P prime is really a subbundle of P And if you think of if you think of every fiber of P as basically a copy of G, what you're saying is that P prime is, instead of taking all the elements of G, you just take the ones that are in H. That's kind of what we're saying here. And now what is probably the most important proposition at this basic level for principal bundles is when can we expect a reduction to exist? So we take our favorite principal bundle, we take a subgroup, Lie subgroup, um, and then we can reduce G to H if and only if, written usually with this double F, there exists trivializing atlas of P with transition functions with transition functions in H. Okay, so this reduced G to H does not exactly how I defined it, but what it means, of course, is that there exists this P prime, which is a H bundle, such that there exists such a morphism. So that's P prime is a reduction of P. That's what we mean to reduce the structure group. And this proposition is telling us that this reduction exists if and only if this bundle P, which had the transition functions with value in G, in principle, actually we can change trivialization atlas to find transition functions in H. The proof is straightforward but pretty involved. In the sense that it's pretty clear what you need to check and what could be a construction. But let's start with this direction because it's a bit easier. So here we're proving that if you do have a trivializing atlas, then there exists a standard reduction. So let's start with this trivializing atlas. So we have H alpha beta from U alpha intersected U beta into H. Thought of it, of course, as a subgroup of G. Be trivializing. Sorry, not trivializing, but transition maps. Be transition maps for P. No. And of course, since now H is a subgroup, we can think of this as some, these are just cocycles. So which means, maps into H would satisfy this cocycle condition. So we can define a bundle out of it. So they define a H principal bundle. And again, this is another name, which just means a principal bundle, which H as a structure group. A principal bundle, P prime on M. And how did this definition come? Well, we had that P prime was this union of U alpha times H modulo this equivalence relationship. And of course, the same can be said for P, because of course we said that this way of writing it is unique up to isomorphism. Yeah, so these are kind of the same thing, but here you have G and here you have H, but they do have the same transition functions. So now what we want to do is show that there exists this reduction. So we define our P prime, we define our P, and we need to find this map H, which is injective. And at the level of single charts, well, I think this is pretty obvious. So we have the obvious u alpha times h. You need to go in u alpha times g. Well, not big surprise. It's just immersion. So, but this is only for one. So the question or the claim is that it passes to the quotient. Yeah, so if you define your map from this union, such that if x is in u alpha, you send xh to just xh, then if you have two pairs which are equivalent, they go to the same thing. So let's see if this is true. We take x g prime, and this is going to be equal to x h alpha beta x g prime. So this is the same equivalence class, and here we think of this pair in u alpha, and this we think about it in beta. Okay, the opposite. Sorry, beta alpha. And this is just something in p prime. Yeah, it's an equivalence class in p prime, and g is just g prime is just in g. But then okay, then we apply this map. And what do we get? Well, here we get x g prime, and here we get x h alpha beta x of g prime. And since this h alpha beta are the transition functions of p, right, then these are really the same. So if we call this, I don't know, this is e alpha. So if we apply e alpha, and here you just get x g prime, and here we apply sorry, this is e beta. And you apply e alpha, then here you get the same. And of course, these are the same equivalence class. So the thing maybe that you have to be a bit worried about, because this seems very much a tautology, is that this equivalence class here are equivalence classes for this relationship, while these equivalence classes here are for this relation. And well, the point is that they're the same. So that's what this claim is about. The fact is that this is just a bit bigger, and in fact, this map is not surjective, but just injective. Okay, so this proves the first direction, because we did find this reduction, so this injective map, which is just the gluing of these I alphas. The vice versa is a bit more complex. That's why I'm going to change page. Yes, yes, absolutely. So we're doing, what was it? This direction. So now we're assuming that, where is it? That we do have such a reduction, and we have to find this trivializing atlas. Okay. So let's say that h from p prime to p is the reduction. And let's take a trivializing atlas, which is both trivializing for p and p prime. Trivializing atlas for p and p prime. And to achieve this, you just take a trivializing atlas for p and one for p prime, and then you just intersect all the open sets. So this shouldn't be a problem. And with the respective, of course, local charts. Sorry, local trivializations, not local charts. So these are local trivializations for p prime. And we have this. So if you take phi alpha p prime of p prime, and this p prime here is just a point. So for p prime and p prime, This is of course going to be equal to some x. So this is an element here times phi alpha prime tilde, I'm going to call it. So it's just, it's two components. The first one is just x, which is pi of p prime. And the second one, I just give it a name, which is phi alpha prime tilde, xp prime. And the thing is that I can think of this p prime as both as a point in p prime, in the bundle p prime, and as a group element. So if I think about it as an element of the group H, then I can just bring it outside by the definition of principal bundle. So you have X, E, this is the neutral element. And again, remember when I write neutral element here, this is an element of P prime, so it's not technically the neutral element of the group, but we're identifying this with the diffeomorphism, okay? Okay. And yeah, this is in P prime X, which we know is diffeomorphic to H. Okay, so now let's take a point in Px, so the fiber over the same x for some x in U alpha. And then necessarily, because the action is transitive, there exists a G in G and a P prime in P prime X, such that this P that we set at the beginning is just the image of the P prime times G. Okay, and this is because this G action is transitive. So whatever point I take here, I can find it with an element of G. Okay. And what I want to, of course, this is not unique in principle, but we do have some properties for, so of what happens if we take some other representative. So let's say that P is also H of P prime 1 times G1. Then what you get is that this G1 prime, well, let's just see what happens. So you see that this G is P composed HP prime inverse. Actually, HP prime inverse composed P, sorry. And this G1 inverse, we again get P inverse, so they cancel out. And what you're left is this. What you're left with is this. But this H, it's a morphism of principal bundles. So I can bring this to inside. And then H was the reduction, so it means that this is an element of H. Okay, so if you have two distinct representatives, let's say, of, so if you think of P represented by this P prime and G, and you have two distinct ones, then this G times G1 inverse is an element of H. And in particular, this gives us that H of P prime is H of P1 prime times G1 G inverse. But now this is an element of H, so I can bring it inside. So this is what we just proved. So this is H, P1 prime, G1, G inverse. But now H is injective. Injective. And because it's a reduction, it's the reduction, we get that P prime is simply P1 prime, G1, G inverse. Okay, so simply P prime G is the same as P1 prime G1. Okay, so even if P and G can be different, P prime and G can be different to represent P, the product P prime times G was the same already in the bundle P prime. In particular, now if we look back at this map, G is phi alpha prime, and we substitute this P with this P1 prime, G1, G inverse, X P1 prime, G1, G inverse times G. But of course, these two cancel out because this is because P prime is a principal bundle. So we can bring things outside. Okay. And again, we can bring this outside. So I prefer to vary like this. Yeah, sorry, because I can only bring things outside things from H. So I bring outside this altogether. Yeah. And when it goes out, the G and G inverse cancel out. So why did I do all of this? Well, this kind of tell us that the map psi alpha from P restricted to U alpha into U alpha times G, which takes a point P and sends it to X, which is of course pi of P, and to phi alpha tilde prime X P prime G, where P prime in P prime X G in G, G in G are such that P is H P prime times G is well be defined. Okay, so this whole computation, which maybe first looks a bit pointless, is to tell that this map is well defined and this is written here. Yeah, it's equal to this whenever you take P equal H P prime times G. And these are local to realizations of P. Okay, so this is a nice injective map, nice bijective map, and a local to realization. And the claim here is that if you now compute the transition maps for this bundle P defined with this transition maps, then we actually get that these transition functions have values in H. And if you just try to imagine it, the reason here is that this G component ends up get discarded and you're left only with this H component. But let's see it. So we take phi alpha beta prime, be the transition functions. Transition functions for P prime. So these are values in H. Yeah. So P prime alpha beta goes from U alpha intersected U beta into H. And of course, what we do have, so observation, is that phi alpha beta prime of X is this phi alpha tilde prime X E times phi tilde prime beta X E inverse. Okay, and the reason for this is that these maps that we started with, this phi alpha tilde prime, were the local trivialization for P prime. So when you compute the phi alpha prime, compose phi alpha prime, phi beta prime inverse, um, this p prime cancels out, and you get exactly this equality. Okay, so now let's go back to our transition functions for p. So we have to compute phi alpha compose phi beta inverse of x t. And here x will be an element of u alpha intersected u beta, and t is just an element of g. Okay. And so if we look at the definition, this is just going to be some c alpha of p, right? And p is basically given by this. But what is p? Is going to be h p prime g. This is just an element of px. P prime is in px, p prime x, and g is in g. Yeah, there's going to be some p here, and this p is just the anti-image under phi beta of xt. But why did I want it expressly? Because by the way phi alpha is defined, this is nothing but phi alpha tilde prime of x p prime g. Okay, this is just a definition of psi alpha. And okay, we can keep going. And now we know. Now the question is, what is this g? And we do have an answer. Because this is nothing but phi tilde prime beta of x p prime inverse times t. Okay, so this is g. And why is this g? Because yeah, if you look, so we have that phi beta tilde prime x p prime times g equal t. And this is just the definition of psi beta. So now that we have this beautiful thing, we can continue. And one very nice thing you can do is bring p out and p out. So x alpha tilde x e p prime inverse phi beta tilde x p prime. Sorry, not p prime, but e inverse t. Okay, and this inverse, of course, means the inverse as a group element. Now these two cancel out, and guess what? We get precisely phi alpha tilde prime xe times phi beta, oh sorry, I forgot prime, phi beta tilde prime xe inverse times t. But this one here, as we said before, is nothing but the transition maps for p prime. In particular, they have values in h. So we see that the transition maps, so if we use this psi alpha as a local trivialization, the transition maps do have in fact values in h. In particular, they're the same transition maps that we had for p prime. And this concludes the proposition. Is there any question about it? I understand it's a bit tough to digest. There's some good 3 pages of proof. So even if you don't have some question now, maybe when you see it again, you have some questions, feel free to contact me about it. So now it's time to maybe understand what this whole bundle, principal bundle is about. And we'll have a first example, which is actually a very general construction. So we take a vector bundle over M with transition functions G alpha beta from the intersection into GLN. Now, if instead of thinking this G alpha beta acting on Rn, we can think of them as acting on GLN itself, meaning that we can use the same transition functions to define a principal bundle. Simple GLNR bundle, which we call PE. So the principal bundle associated to the vector bundle E. And how do we obtain this? Well, we know that if you have something which satisfies the co-cycle conditions, then you have a given fiber, in this case GLN, then you can make a principal bundle out of it. And that's it. That's the one, P. The vice versa also holds. The vice versa holds. So if I have a principal GLNR bundle, there is a unique, and of course this uniqueness is up to isomorphism, vector bundle associated to it. The vector bundle E such that P of E, let's give it a name. If we have P, so P of E is P. Okay, so there is a unique up to isomorphism bundle associated to it, and you can just go back and forth with this thing that these are just functions in GLN, so they automatically define both a vector bundle and a principal bundle with fiber GLN. Okay, so now we're gonna have a proposition which is gonna be very important in a few weeks when we talk about the Picard group of a complex manifold. Because of course, now we always spoke about real objects and smooth maps, but we can do again all of this with holomorphic objects and everything works just fine. But there's this particular construction which is this particular definition, which is more relevant for complex manifolds. So we start with a manifold, so not necessarily complex, and we take a vector bundle over M with fiber CK. So now we have a complex fiber. And structure group GLKC. And in this case, we say that E is a complex vector bundle of rank K. Furthermore, if M is a complex manifold and the transition maps, sorry, not the transition maps, and the projection is holomorphic, then we talk about holomorphic bundles. So to talk about complex vector bundles, we just replace R with CK, so R with C, and we ask that the maps are C-linear. Okay, so the structure group GLKC means that the maps are C-linear, just not just R-linear anymore. And Furthermore, if this map is holomorphic, so to even define holomorphic, you need M is a complex manifold. We call this E a holomorphic bundle. And holomorphic bundles of rank 1 are particularly interesting. So with fiber just C. So let's take two holomorphic fiber bundles. So holomorphic bundles of rank 1. So these are usually called the line bundles. Line bundles. For obvious reason, yeah, these are rank 1 means a complex line. So on a complex manifold M, and let's take the transition functions with G alpha beta, G alpha beta prime, transition functions, respectively. And then the question is, when does a bundle isomorphism exist? Then there exists a vector bundle isomorphism f from L to L prime if and only if for every alpha there exists an F alpha from U alpha to C star holomorphic such that if you take the quotient F beta over F alpha restricted to U alpha intersected with beta, otherwise it doesn't make sense. This is the same as G alpha beta over G prime alpha beta for every alpha and beta. I'm going to discuss it in a second, but first I'm going to give you the proof as exercise. As exercise, maybe it looks a bit hard, but you just have to look at, we already did this for general bundles. So we have a proposition where you have just two vector bundles of any rank, and we know that they are equivalent, so they're isomorphic to each other if and only if some functions exist. And the fact here is that everything actually becomes easier. Because we have rank 1, so instead of having like F beta times the inverse matrix of F alpha, you simply have F beta divided F alpha, and the same here. Because this G alpha beta, in their transition functions of rank 1, they're simply non-zero complex numbers. Okay. And maybe one small observation here is that so L is trivial if and only if there exists this F alphas such that F beta over F alpha is G alpha beta. Yeah, because trivial means C star. Trivial means, of course, that you're just M times C. So your transition functions, you can think of them as being identically 1. So you get this. Okay, and the interesting, basically what it's telling you is that this G alpha beta is defined only in the intersection, but you can separate it as a quotient of something that lives on U alpha and something that lives on U beta, and which are never 0. This is important. So for those of you that took a course in complex analysis, this is actually Cosen's second problem, if you ever heard of it. But just this simple expression here has been studied actually independently of this all bundles thing. Okay. Any questions so far? Okay, if not, it's time to, so we define the bundles in general, we define vector bundles, and we define principal bundles. So now I want to work with some specific vector bundles and some specific principal bundles. And of course, the first one that comes to our mind is the tangent bundle of a manifold. Okay, so we already defined the tangent space in a point. And then we define Tm just by the disjoint union, this TPM is the tangent bundle of M. And proposition Tm into M is a vector bundle of dimension equal to the dimension of M. And furthermore, if phi alpha beta from phi beta u alpha intersected u beta to phi alpha u alpha intersected u beta are the transition maps for M. Yeah, so so this is a local, so this phi alpha and phi beta are the local charts. So this phi alpha beta is just the composition of phi alpha composed phi beta inverse. So if these are the transition map for M, then the transition maps for the bundle is given by, we send P to the matrix of the differential d phi alpha beta at the point P in the standard basis, in the standard basis of Rn. Yeah, you know, a differential in principle is just a linear map between some spaces, but then if you actually fix a basis in the domain and codomain, then this gives you a matrix, and then we take that matrix. And it turns out that this matrix is precisely the one that gives you the transition maps for the tangent bundle. We will not give a proof of this. I believe you've already seen it, or at least you know enough to go find it yourself if you've never seen it and you're interested. But it's mostly just tedious. I think it's pretty obvious what you need to check, what you need to do. But then you have to do it, and that just takes some time. And as an exercise, which maybe is a bit more interesting, prove that Tm is orientable always. So what does it mean by this? We know, so we defined what it means for a manifold to be orientable. And the point is here that Tm is a manifold itself. Yeah, we say that this space, this total space is a manifold, needs to be a manifold. And yeah, you have to prove it that as a manifold, it is orientable. So as we said before, every time you have a vector bundle, just like the tangent bundle, you can associate to it a principal bundle. So let's see what happens when we do it, when we start from the tangent bundle. We obtain a thing which is called the frame bundle. So we start with a manifold. Vector bundle on M of rank R. And now for P in M, let F of E, which of course stands for frame of E, at P, be all possible ordered bases of EP. So EP, this is a vector bundle, so EP is a vector space, so we can talk about bases, and not bases just a set, but ordered bases. So I care about which one is the first, which one is the second one, and blah, blah, blah. And we define this FE as the union over P, it's joint union over P of these possible bases. And with, of course, the projection is what you expect it to be. If you take a collection of bases V in Phi E P, well, this one goes to P. So this is the frame bundle. Okay. And as I said before, this should be a principal bundle. So let's prove it. So FE is a principal bundle with fiber GLR M. R is the dimension of E. Sorry, not M. GLR R, which is equivalent, and not just as a bundle, but really as a principal bundle, to what we described before as P. Okay, so the difference, let's say, between this FE and PE is that PE was more defined abstractly. You just take this transition function and you say, okay, we make a principal bundle out of it. While here, this one has a more geometric interpretation. You just start with some abstract transition functions. You really say, okay, I take ordered bases. And so what we have to prove here is just that if you take the transition maps, transition functions here, you get exactly, well, basically the ones from E. Okay. So let's prove that. So how, first of all, how do we act? So GLRR acts on the right on FEX as follows. So we take A in GLR R, and we take this W underlined. With this I mean ordered collection. Yeah, think of this as a, so WR. Think of this as just a point in the frame bundle. Sorry, I'm gonna use P. So X. B on order basis of EP. So each of this is a vector in EP, and they're linearly independent between them. And now we define R A W. So this is our right action as the transpose of A applied to W. So this A is a R times R matrix. So non-singular, the transpose again is a R times R matrix. And we apply to this. But what do we mean? Because normally you apply things not to, you apply things to a vector, not to a collection of vectors. So what we mean by this is the collection of vectors, because I need to get a new collection of vectors, is sum in I of A I1 wi, comma, 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 sum in I of ai r wi. Okay, so this is again a collection of r vectors. And because you see each one of them, so this first one is a linear combination of this ones, and the last one is a linear combination of this ones and all the ones in between. And the fact that the matrix A was non-singular tells you this is still a basis. Okay, so in particular, it's an element of FEP. So this gives us the action in this abstract way, but we saw that even in the previous propositions, we always needed somehow to identify some neutral element in the fiber. Okay, the point is that again, this fiber is not a group. It's isomorphic to a group. It's diffeomorphic to a group, but it's not a group by itself. So somehow we have to artificially say, okay, this is our neutral element. And in our case, since we have local trivialization of E, the best thing is just to import the standard basis of Rn. So let us import the standard basis for R actually. So we take a trivialization of E, B, local trivialization of E near this point P that we fixed. Near P just means that P is new. And define Vj of P as simply the anti-image of Ej. And of course, Ej is nothing but the standard basis. Okay. In particular, this means that what I'm going to call V underscore, which is V1 of X. Sorry, this should have been X comma Mj. Yeah. Okay. Vr of X. This is an element of F E X for every X in U. And furthermore, if we take another one, so let's say if we take U in F E X, no, sorry, F is the same, but for consistency, there exists a unique element of GLR R such that U is A transpose V. And in particular, this gives us that the pi inverse of a point is diffeomorphic to GLR R. Okay, so this is already a first step into proving that this is indeed a principal bundle. Okay, yes, we were trying to define some local charts here. So define H from pi inverse of U into U times GL R R, which takes one of these sets and sends it, of course, to pi of U, as we defined before, psi of U. And what is psi? Where psi of U is the unique element of GLRR such that U is psi U transpose. of V. So this is kind of how we give this diffeomorphism with GLR. We say that there is a unique matrix that does this. Well, let's just take it. So as I was saying before, this is kind of artificially saying that our V, so the basis coming from the standard basis, is the identity element. Yeah, because then it just becomes V equal V and A is identity. Okay. So I'm not going to verify that this is a principal bundle. The thing I want to do here now is find the transition functions. We now compute the transition functions. And why do we want to do this? Of course, it's because this our FE was defined somewhat naturally, but it's not clear what are the transition functions, not clear that it's a principal bundle. So now we know that it's a principal bundle, or at least after this exercise, you know that it's a principal bundle. And to prove that it is the same bundle as this PE, where is it? This PE that we defined in the previous slides, we have to compute its transition functions and show that they're the same. Okay, so now we take U alpha, U beta with non-empty intersection. And let's say that phi alpha and phi beta are trivializations for E, for the bundle E. Okay, so we can mimic this thing again. And we have Vj alpha of X, which is phi alpha inverse of X Ej, but we also can do the same for beta. Okay, so it's the same thing we're doing here, but we're doing it in both sides. And now if we take V in Ex, then this can be written in two ways. As the sum over J of some Aj Vj alpha of X, but also as the sum over J of Bj Vj beta of X. And furthermore, we know that this A1 AR is nothing but G alpha beta of X times B1 BR. And just G alpha beta are the transition for E. Yeah, so this is all for E. So from linear algebra, what you get is that V1 alpha of X, VR alpha of X, so as vectors, this is G alpha beta of X to the negative T, meaning the inverse transpose or transpose inverse doesn't matter, commutative. VR beta X. And this is something that is very, let's say, very easily forgotten. But if the coordinates vary with this matrix, then the vectors themselves vary with the inverse transpose. So this gives us that phi beta view, and this of course psi beta is the one that we used to make this trivialization, transpose of V beta, which is just U, is the same as phi alpha U transpose V alpha, and there is no difference here. I don't know why I made squares on one side and round on the other. Maybe square just to remember that it's a matrix. But here now we can use this fact. So this V alpha is just this collection of all of this, right? So we can use this. And we know that this is the same as G. So this would be G alpha beta inverse, yeah? Because transpose and transpose cancel out, V alpha. But you know from the cocycle conditions that this is just the G beta alpha of X times V alpha, okay? So what this means is that when we use this H here, we do H alpha composed H beta inverse of X comma psi alpha of U, what you get is X comma G alpha beta of X times phi beta of U. Sorry, not phi beta, but phi alpha. And this is psi beta. And so the transition functions are the same, are this G alpha beta. Okay, so transition functions are the same. So in the end, it turns out to be some lots of linear algebra. There's only one thing that we have to check. So transition functions are the same tells you that this is the same bundle. It doesn't tell you that it's the same principal bundle. So we have to check. We only have to check that this H alpha are morphisms of principal bundles. Yeah, because having the same transition function just tells you that you're the same bundle, not the same principal bundle. So how do we check if something is a morphism of principal bundle? Well, we have to check that the right action comes out. Yeah. So let's compute it. Okay, this by definition was this. And okay, but now this is a generic U. So we can write it in terms of our identity, meaning in terms of our standard basis. So this is phi alpha U transpose times V alpha. But now we can put these two together. And here we get H alpha of phi alpha U A all transpose V alpha. But yeah, but then if we apply our trivialization, yeah, this H alpha, where was it here? Here we get the unique matrix such that this is true, and the unique matrix is exactly this one. So what you get is X comma C alpha U times A. Okay, so this in particular gives that this is the correct right action, because the right action here becomes the right action here under the map H alpha. Okay. Okay, so to take a step back, let's go back to the statement. And we define this frame bundle as this set of ordered bases. And what we proved is that this is actually the principal bundle associated to the vector bundle E. And of course, we have a very fancy, let's say, a very important frame bundle, and is the one you get when the vector bundle you start with is the vector bundle, is the tangent bundle. So when E is Tm, we just write Fm for f of Tm. Okay, so we just write the frame bundle of M. We don't write the frame bundle associated to the tangent bundle of M. And now there is what I think is actually a very nice exercise because it links things we know from before to this new language. So for now, this is like, it is new, but most of all is a new language. And we will see the power of this language in a bit. But so let's take with, we start with the smooth manifold. Of dimension n, then Fm admits a reduction to GLNR plus, and that is the set of matrices in GLN that have a positive determinant, if and only if M is orientable. Yeah, so I think this really shows how all this new language about bundles, principal bundles, is helps encode some information that we were already studying. So for instance, orientability is equivalent to asking that a certain principal bundle admits a reduction. Okay. So I want to go quickly through some other examples of principal bundles, and then we will be done for today. So other examples. So take this. So we take SON into Sn minus 1. And so I take a matrix A, which I think has a bunch of columns. Yeah. And being in SON means that each one of these columns has a modulus 1, and that they're orthogonal to each other. And this S also means that this is a positively oriented basis. And I just send this to the last column. Yeah, so I was saying they have these are just the vectors in Rn, and they each have norm 1. So in particular, they lie in this sphere. So it's well defined. And surjective, simply because I take a point here, and then I just complete the basis to an orthonormal basis, for instance, using Gram-Schmidt. And observe also that Sn minus 1 is just the anti-image of 0 for the map that takes a vector x and send it to x times x minus 1. In particular, this gives us that the tangent space at a point is all the vectors that are in the kernel of this f, of the differential f. But this is, if you think of P just as an element of Rn, this is actually the same as V times P. Okay. So in particular, if A is, again, we write it like this. So this is a matrix of n columns. Then A1, An minus 1 is our orthonormal basis, orthonormal basis of what? Of the An Sn minus 1. Because see An is replaced, and this is and since this A is in the SON, these are all orthogonal to here, and they form a basis. And let's denote by the okay, so let's denote it by u underscore A. Okay, so with this u underscore A, we denote the basis of TAN Sn minus 1 given by A1 An minus 1. And of course, this is an element of the frame bundle. Okay. So let's now take an atlas. That now you have an atlas of Sn minus 1 such that E1, En minus 1 is a positive basis for D En Sn minus 1. So what it means, positive basis, you know, you can, once you have two bases, you can say that they have the same orientation or that are different orientation. And if you want to specify which one is the positive orientation, you just pick a base and say, okay, this one and everything which agrees with this one is the positive orientation. Okay, so this of course gives rise to a basis on U. So this gives rise to a basis made by derivation d dx1 alpha at b, comma, 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 d dx alpha n minus 1 b. This is a base over U. And this basis can be changed to an orthonormal basis, to a positive orthonormal basis, which I'm going to write as V alpha at B. What I mean by change to orthonormal basis, you know that every time you have a basis and a scalar product, by using the Gram-Schmidt algorithm, you can find an orthonormal basis. Yeah. And this is what we do. And the interesting thing is that when using the Gram-Schmidt algorithm, what you're using, it's only the scalar product. So everything is smooth. So this is our normal basis VP depending smoothly on P. Smoothly on P. In U. P in U. Just in U. Okay, so what about this? What do we do all of this? So if you start with one of these bases that we were talking about before, then there exists a unique A alpha, and this is a matrix not in SON, but in SON minus 1, such that U of alpha is A alpha transpose B alpha AN. So at the point AN, yeah. So this gives us that the fibers are SO N minus 1. And trivializing functions, C alpha, they go from phi inverse U alpha to U alpha times SO N minus 1, go from A to AN A alpha. And now basically using the same proof that we did before with this frame bundle and versus principal bundle associated to it, you can see that so it is possible to prove with techniques that we've already seen that the transition functions have values in SON minus 1. So what is what did we prove here? Is that this projection SON into Sn minus 1, which takes the last column and gives it, just takes the last column, is in fact a bundle, and it's a principal bundle with fiber SON minus 1. Okay. Okay, so this is an example. Let's give another example, or maybe, yeah, it's just two more examples. So I will finish a bit late. Another interesting example is the hop fibration. And it's a map from S to N plus 1 into CPN. So you think of this S to N minus 1 as the things of modulus 1 in C. So you think of this as something in C N plus 1. Yeah, so if you take everything of modulus 1, this is simply S to N plus 1, and you send it to the corresponding point in CPN. Turns out this is also a principal bundle with fiber S1. So this is the hop vibration, and so this I'm just telling you this. This is not something we'll prove, but as an exercise, prove it for n equal 1. Yes, and why for n equal 1 is particularly interesting, because this is simply S3 into S2 from a geometric point of view. So if you think CP1, you can think of it as the so-called Riemann sphere. So you can think of it just as a sphere. So what we're saying here is that you can imagine this hypersphere as locally, just locally, as S2 times S1. Okay. Okay, last example. Not gonna do everything. I'm just kind of gonna tell you that homogeneous spaces, Neos spaces, are also such examples of principal bundles. So if G is a Lie group and H is a subgroup, Lie subgroup, then G goes to G mod H, the projection is a principal bundle with structure group H. Okay, and okay, of course, now I mean, I should prove this, but it's not essential that we see the proof of this, and running a bit out of time, but I think it's easy to imagine. Of course, it's obvious that the fibers look like H, and I let you imagine how you can prove that this is the correct one. If at some point you want to see it, just let me know, and we will see it together. Otherwise, thank you for coming, and I'll see you tomorrow.